Mr. Ellinger here. This lesson is on probability models. Our learning target is to use probabilities to make fair decisions and analyze decisions. Essential understanding for the lesson: probability models can be used to analyze situations and make fair decisions. Some background for this lesson: learning how to model random situations and make fair decisions is an important skill that can be applied in many areas of life. You likely have been developing these skills by doing things like flipping a coin to decide who gets the ball first in a game, for example. A probability model is a mathematical representation of a random situation. A simulation is a probability model that uses probabilities to make predictions about real-life situations. A probability model can give you insight into what should happen mathematically so that you can make better decisions. So we can use probability models to analyze situations and make fair decisions. Like we said, a fair game is a game in which all of the participants have an equal chance of winning. For example, two players take turns rolling a number cube, or a die. The first player gets a point if an odd number is rolled, and the second player gets a point if an even number is rolled. Each player has the same probability of scoring a point on each roll, so we call that a fair game. Similarly, a fair decision is based on choices that are equally likely to be chosen. So let's look at an example here. Two siblings are trying to decide who has to mow the lawn this weekend. They decide to race, and the winner does not have to mow the lawn. Is the result a fair decision? Well, this takes a little bit of thought. We don't really know anything about the siblings, but it would probably help if we did, right? What if the two siblings, meaning brothers and sisters or two brothers or whatever, what if one was 15 and one was 5? Now, granted, a 5-year-old's not going to be mowing the lawn, but let's just consider it. If one's 15 and one's 5 and they're going to race, who's going to win? The 15-year-old's going to win. So we don't really know anything about the siblings, but what we have to go ahead and assume is we have to assume that this is not a fair situation. Okay? So we would say not fair. The only way that it really would be fair is if the two siblings were of identical athletic ability, essentially the same running speed, and then whoever wins, that would be a fair game or a fair decision. So is each sibling likely to have an equal chance of winning the race? Not unless what I just said. Unless they both have the same athletic ability, same running speed and whatever, that's not the case here. So we would say it's not fair. All right, so we can use a probability model to assign probabilities to outcomes of a chance process. A couple lessons ago, we learned that you can use a simulation to estimate the experimental probability of an event. A simulation is an example of a probability model. You can use probability in simulations to make predictions about real-life situations. So I just have some examples here with answers. Let's just go ahead and look at the first one here. To decide who has to mow the lawn, two brothers flip a coin. If it lands on heads, Tony has to mow the lawn. Otherwise, Chris has to mow the lawn. Will this result in a fair decision? The answer is yes, because each brother has the same chance of having to mow the lawn. Flipping a coin, heads and tails are both equally likely. So that would be a fair situation. All right, our middle box here. Suppose a manufacturer is giving away 6 different prizes in boxes of cereal. The prizes are randomly and equally distributed in the cereal boxes. Describe and conduct a simulation to predict how many boxes of cereal you would need to buy to get all 6 prizes. Well, anytime we want to do a simulation, we always want to look at how many outcomes are there. And in this case, there are 6 prizes. So we need a simulation that has 6 outcomes. Okay? So sometimes flipping coins is going to be appropriate, other times not appropriate. We need to think about what types of things can we do that have 6 equally likely outcomes. In this case, a number cube or a die, a standard die, would be the best choice because it has 6 sides, and all the sides are equally likely. So we could roll a number cube and let each number represent a different prize. Now, the simulation results are going to vary. Okay, when you actually do the experiment, remember, experimental probability doesn't always turn out the way theoretical probability says it should. Another way that we could do this is we could take a spinner Okay, a spinner, we could divide it up into 6 sections, make sure all the sections are the same size, and then spin that spinner, and that would also be a way to simulate this, okay? So spinners, rolling die, flipping coins, those are usually our most common basic forms of simulations. Definitely not the only way to do simulations. We can have random number generators and things like that. All right, another example. Some junior varsity football players choose to participate in the voluntary weight training program over the summer. The table shows the results of who made the varsity team the following year. Based on these results, would you recommend the weight training program to junior varsity players? Well, let's take a look at our table. So, made varsity, we had 7 that did weight training and 2 that did no weight training. Out of the ones that did not make varsity, 5 did weight training and 6 did no weight training. And we had 20 total players. So we would conclude, yes, those who attended the program had a much better chance of making the varsity. 7 compared to 2 with weight training made varsity. 5 compared to 6 did not make varsity. Okay, so here we have an example. Got a table with some data here and some information. We have a pharmaceutical company is testing the effectiveness of a new drug for asthma patients. Out of 160 volunteers who suffer from asthma, 80 are given the drug and 80 are given a placebo, which has no active ingredients. After 2 weeks, the volunteers are asked if they noticed improvement in their asthma symptoms. The results of the survey are shown in the contingency table at the right. So remember, a contingency table over here to the right is basically a two-way frequency table. Okay, so we have an improved column, and we have a did not improve column, and we have a totals column. So received the drug, 67 improved, 13 did not, 80 total patients. People that received the placebo, 24 improved, 56 did not improve out of 80 total people. So in total, we had 91 people that improved, 69 people that did not improve, and 160 total in this test. Okay, so question A, what is the probability that a volunteer reported noticeable improvement in symptoms given that he received the test drug? Well, the first row represents the total number of volunteers who received the drug. The number of those volunteers that reported improvements in symptoms is 67, so that's our numerator. And our probability, that's our favorable outcome. The number of those volunteers who received the drug, total number of volunteers who received the drug, was 80. So 67 out of 80 is the probability that we need to calculate. And when we calculate that, we get a value of 0.8375, and that's about 84%. Part B, what is the probability that a volunteer received the placebo given that he did not report a noticeable improvement in symptoms? So given that they did not improve, so we're talking about this column here, what's the probability that they received the placebo? That's this value right here. So that is our favorable outcome. That's the top of our fraction, our probability here, 56. The total number that did not improve was 69. So our ratio is 56 over 69, which is 0.8116, or approximately 81%. Part C says the pharmaceutical company decides to produce and distribute this drug. The drug is marketed as an effective way to improve the symptoms of asthma. Based on the results of the test, did the company make a good decision? Well, if you take a look here, if you received the drug, 67 people improved out of 80. So you have to decide if that's good or not. So the probabilities calculated above show that about 8 out of 10 people who are given the drug experience improvements in symptoms. Also, about 7 out of 10 who receive the placebo do not experience improvements in symptoms. Based on the study, the new drug appears to be effective at treating asthma symptoms, so the company made a good decision. So they're basically saying because so many people that got the drug improved, and so many people who didn't get the drug did not improve, those two things, they went ahead and stated that the company made a good decision. And I would probably tend to agree. Have a good day, folks.